Welcome to qnawire.
Hello, today I'm going to be solving a problem where we figure out the average angular acceleration of a potter's wheel as it is spun from rest up to some final angular speed of 1 revolution per second. After that, on part B, we'll talk a little bit about what would happen to the final angular speed if we change the average angular acceleration. So let's start with part A, finding the average angular acceleration. So first, we have to think about what the problem gives us. So from the problem, we are told that the wheel starts at rest, meaning that the initial omega or initial angular speed is equal to 0 radians per second. And then the problem also states that the final angular speed is 1 revolution per second, but it wants our answer in radians per second squared for the average acceleration. So I converted this into radians per second rather than revolutions. So what I did to do this was I thought about, okay, 1 revolution, what does that mean? So a revolution, let's say I start at this point on the circle, means that I have gone all the way around the circle and I came back to my original spot. And I did that on the circle. I'm not drawing it on the circle just to be a little bit clearer. But that is 1 revolution. So then if you translate this into radians, you can think about 1 cycle for radians is always going to be 2 pi, or 1 trip around the circle is going to be 2 pi radians. So then I have multiplied by 2 pi to get my answer, or to get my given number in radians per second instead of revolutions per second. And then finally, the problem also gives you the time it takes to accelerate up to that angular speed. So that is given to us as 30 seconds. For our first part of the problem, the formula we're going to need is the definition of angular acceleration, which is a change in omega or change in angular speed divided by the change in time, or how long it takes to accelerate up to that final speed. And then we also need to define that change in omega equals the final omega minus the initial omega to get our change from the beginning to end. So I will combine these 2 equations here to get us an equation: alpha, angular acceleration, equals the final angular speed minus the initial angular speed, all over the time it takes to accelerate up to that point. Notice that I've dropped the change. That is just because it's easier for us to think of time as just this is the time it took, instead of thinking that, oh, it started at time equals 0 and then it ended at time equals 30. Just makes it a little bit simpler. So then I'll plug my numbers in, and I have 2 pi radians per second minus 0 radians per second. And I will divide that whole thing by the 30 seconds it took to accelerate to that speed. And what I end up getting for that answer when I plug it into my calculator is 0.209 radians per second squared. So that is my answer for part A. That is the angular acceleration of that wheel as it gets up to the speed we were told in that amount of time. And then for part B, it asks, okay, now let's say we double your angular acceleration. So let's say if alpha equals 2 alpha, or double our original speed up here, we don't even have to plug in numbers for this. Then I want to know what my final angular speed would end up being, because it wants to know if that final angular speed would also double. So what I'm going to do is first I'm going to start over here with the formulas I need. We're going to start with the angular acceleration formula, which is change in omega over change in time. So I'm going to write that down. And I'm going to even skip ahead because we know that equals alpha final minus, or it equals omega final minus omega initial all over t. And we know that this number here is still going to be 0. We are still starting from rest. We don't need to worry about that value. So if I want to find omega final, I'm going to multiply both sides by t, and I'm going to get the final angular speed in general is equal to alpha times t. So that is my general formula. So now I have to take into account this part. If I say I double my alpha. So if I double my alpha, I have to look at omega final equals 2 alpha times t. And now we have to think about what this actually means. So if we look at our answers, okay. So what we're looking at now is that this red final, or the new final, is equal to, let's write this in black now, 2 times alpha times t. And we can say that this alpha t from before is what we got for our first answer. So our omega final in blue. So if we look at that closer, we can see that this equals 2 times whatever value I got to begin with, which is the blue omega final. So that means that our final angular speed is going to be 2 times whatever I started with because of this double acceleration. So that means that, yes, the final angular speed will double because we doubled the angular acceleration.